Hi, my name is Julia Fleischman, and today I will be discussing the motion of a falling object for my Lab 2 report for Physics 1. In today's report, I'll introduce the procedure and purpose, then discuss my experimental findings and then my computational findings. After that, I'll compare the two models to then conclude my observations and answer any remaining questions. The purpose of today's lab is to observe an object's motion that is dropped from rest. We'll observe the effect of both gravity and drag forces on a falling object, create an experiment, model the experiment through code, and compare the models. Some fundamentals that will be featured in today's report is Newton's second law with a net force that is not zero. This can be represented as the velocity update formula, which is Vf equals Vi plus F net divided by m times delta t. We then also implement the equations for gravity and drag force. The force of gravity equation is negative mg times j hat, where m is the mass of the object, g is the gravitational constant 9.8, and j hat represents the direction of which the object is traveling. We also have the drag force equation, which is negative b times the absolute value of v squared times v hat, where b is the proportionality constant, absolute value of v is the object speed, and v hat is the velocity direction. In my experimental model, I used tracker to observe the effects of gravity and drag on a falling glue stick. Here, the system is a glue stick and the surroundings are everything around it, like the floor, the air, and my hand. The initial conditions for the experiment are that the initial velocity is 0 and the initial position is 1 meter in the positive y direction. It takes the glue stick approximately 0.533 seconds to hit the ground. And the result is that the computational model with drag predicts the experimental model more accurately than the computational model with no drag. In my experimental model, I used tracker and I was able to record the motion of the glue stick over time, and the software created a graph to represent its motion. After tracker input the collected data into a table, it created one graph representing the glue stick's x position over time and a graph representing the glue stick's y position over time. For this report, we will only use the y direction versus time graph, which can be seen at the bottom. In our experimental model, we can see that our object's position respective to the y-axis is gradually decreasing over a time frame of around 0.5 seconds. I then used the GlowScript software to computationally model the position and speed of the glue stick. The expo marker's mass is around 0.008 kilograms, and I inputted the initial conditions that were just shown on a previous slide. Our delta t is 0.033, which represents our time step from the tracker. This computational model will model the motion of the glue stick without applying any drag force, so the proportionality constant is 0. In the while loop, since our net force only includes gravitational force, our equation is negative mg times gravitational constant times j hat. We then use the velocity and position update formulas to analyze the glue stick's velocity and position over time. When this code is ran, we can see that the glue stick's position gradually decreases over time and our velocity remains constant because only the gravitational force is considered in this model. When we compare the no-drag computational model and the experimental model, we can see that in the experimental model, our glue stick's velocity eventually decreases, whereas in our computational model, our velocity remains constant. To create a more accurate computational model, the net force equation was modified to make the net force equal to the gravitational force and the drag force combined. The variable b represents our proportionality constant, which was calculated to be 0.17. When we graph this new computational model, we can observe that the object's velocity is not constant and therefore does eventually reach a stopping point. This is due to the drag force that we included in the model. To visually represent this, a graph was created comparing all three models, the two computational models and the experimental model. It is notable that the computational model that included the drag force better predicts the experimental model. The discrepancies between the red and yellow line are due to my errors while using the tracker software. When I was tracking the glue stick's position, I tracked the bottom of the glue stick instead of the middle. This is why the computational model sometimes undershoots and sometimes overshoots the experimental model. In future experiments, I'll make sure to track the center of the object rather than an extremity. So now we ask ourselves, do any of our models predict a terminal velocity? And the answer is yes. Our computational model that includes the drag force shows deceleration, which indicates that there is a speed that cannot be exceeded, which is our terminal velocity. Well, what if the glue stick was additionally thrown downward? The graphs of velocity would be the same as the glue stick being initially drop from rest because acceleration in this case is still decreasing. The only difference is that this object would most likely decrease its acceleration more rapidly. These observations then led me to a conclusion. The effects of gravity and drag forces cause a falling object to eventually reach a stopping point, and when gravitational force is only present, velocity remains constant. However, when both gravitational and drag forces are present, an object's acceleration will decrease and cause its velocity to become terminal. Thank you.